Hello, AP Physics students. This is going to be kind of a two-part video here. I'm going to talk about impulse and momentum just a little bit before we dive into an example problem. And the example problem is going to be from chapter number 7, and it's going to be problem number 4. Okay? But before we dive in there, just some background information. Okay? This chapter is about momentum, and we use the letter P to represent momentum. What is momentum? It is mass in motion, and it is defined as mass times speed. Notice it's a vector quantity pointing in the same direction as the velocity. And its units are kilograms times meters per second. Now, why is this new idea important? Because it turns out if there's no external forces acting on a system, momentum will be conserved. So the initial momentum and the final momentum of a system will be the same if there's no external forces acting on the system. Okay, so much like conservation of energy was a powerful idea for chapter 6, conservation of momentum is going to be a very powerful idea in chapter 7. Matter of fact, they're very powerful ideas in all of physics. Conservation of energy and momentum is how we discovered many new subatomic particles. Okay, so this is an important definition. This conservation of momentum is an important idea. And the last kind of new idea is this. Newton actually defined a force to be the rate of change of momentum of an object. The larger the force acting on an object, the greater its change in momentum would be, okay? So this idea of, the net force acting on an object will be equal to the rate at which the object's momentum changes, okay? So that's chapter 7.1 and 7.2 in a nutshell. But let's apply these ideas to something, okay? So let's apply these ideas to problem number 4 in chapter 7, okay? And this problem deals with conservation of momentum. So I'm going to kind of do a bit of a before drawing and an after drawing, okay? Before and after. So the problem states that I have a boat and it's in water, right? So, ooh, look, I brought just for you physics students, I brought my blue pen. Oh, look at those water waves. Oh, they're gorgeous. All right, good stuff. All right, so before I have a system at rest, and it's a boat with a child in it, and the child is holding a package, all right? So really, the before is not very interesting. The initial momentum of my system is 0, okay? Right? The boat, the child, the box, they're all sitting at rest, okay? Okay, but let's define some things here. The problem tells me that the mass of my boat is 45 kilograms. The mass of the child is 26 kilograms, and the mass of this package is 6.40 kilograms. Okay? Now, what happens in this problem? Well, the child throws the package. All right? So maybe the package contains a physics book, right? And the child gets frustrated and throws the physics book. Well, what happens to the child boat system when the package is thrown that way? Well, this system kind of recoils this way, okay? Now, since there are no net external forces, okay, the final momentum of my system is equal to 0. Now, I know what you're thinking, but Mr. Kirsten, doesn't the package have momentum going this way? Well, yes, it does, but remember, momentum's a vector quantity, so the momentum of this package plus the momentum of this guy is going to kind of cancel out, okay? And I can say this because there are no net external forces acting on the system. The system being the boat, the child, and the package. But Mr. Kirsten, isn't there a net force of gravity? Isn't gravity outside the system? Isn't that acting on it? Well, yes, it is, but gravity is being counteracted by the buoyant force on the boat. So while there are external forces, there's no net external force. Okay? So let's go over here and let's see if we can't use this information to solve for what the problem's asking for. That is, what is the recoil speed of this child boat system this way? By the way, oh boy, I didn't include this. The problem tells us that the velocity of the package after the throw is 10.0 meters per second, right? So we should include that. And of course, before I start writing equations, right, I should define a coordinate system. So I'm going to say to the right is the negative x direction and to the left is the positive x direction, right? Boy, why did I do that? Why would I do that? How about I make to the right positive x and to the left minus x? Because that's traditionally how we do it, right? Yeah, what am I thinking? Okay, so let's use conservation of momentum. The initial momentum of the system should equal the final momentum of the system, right? What's the initial momentum of the system? 0. What's the final momentum of the system? Well, it's also got to be 0, but it also has to be equal to the mass of the package times the velocity of the package, right? So the momentum of this guy this way, right? Plus the mass of the boat plus the mass of the child, right? I'm treating this as all one object, right? Times the velocity of the boat child, okay? Now, let's kind of look at what our signs are going to be. The momentum of the package should end up being positive, and the momentum of the child boat should be negative, all right? Okay, well, let's plug in some numbers and see what we get here. So 0 should be the mass of the package, 6.40, all right, times the velocity of the package, 10, all right, plus the mass of the boat child, right? So that would be 45 plus 26 times the velocity of the boat child system here, right? Okay, so let's do a little algebra here, right? And I would get, this would be 64 moved to the other side. I get negative 64 is equal to 71, adding these up, times the velocity of the boat child system, divide by 71 there, and I would get the velocity of the boat child system is equal to a negative 0.901 meters per second. And for emphasis here, I might say away from the package, right? Okay, so this negative sign here indicates that the boat's moving this way in my negative x direction, right? So the boat child system is moving away from the package, right? So this is a problem here where we use conservation of momentum to solve for some missing variables here. So conservation of momentum, a very powerful idea. All right, so we got a cartoon coming up here to give you a little laugh for watching here. All right, here's our cartoon. We got a skier going down a hill. It says laws of gravity strictly enforced here. Oh, that skier's going to encounter some gravitons, which are going to pull them to the bottom of the hill very quickly. Hopefully they put a wax on their ski, which greatly reduces their coefficient of kinetic friction so they can get to the bottom of the hill really, really fast. All right, thanks for watching, AP Physics students.